Hi guys, so today we're going to go over some interesting problems. These are problems for AP physics, but it could be also for mcat physics. It's very similar questions. You have the PDF here on that website, so I will put that link in the description below. So we stopped here. I think here, so those ones here I'm skipping, but you see that you have pendulum, and if they ask you to find which one will oscillate with the lowest frequency, remember that the period or the frequency of a pendulum only depends on its length, right? So the short length will have the smaller period, so the largest frequency. So the lowest frequency will means the larger period will be the longest pendulum. Okay, so number 14, interesting also, typical conceptual equation. So what do you think about, so those are two pulses, but this one has small amplitude, this one has a large amplitude. So which one will travel the fastest? You can pause the video, but we don't have enough information because the speed of a pulse or a wave on a rope only depends on the tension, which is the restoring force, and the mass, the mass per unit length. It doesn't depend on the amplitude. The amplitude has to do with the energy that the wave will carry with it. Okay, so another question they like, typical conceptual equation. This one, let's look at this one, number 15. So you want the wave pulse to travel twice as fast. So it means you want the speed to be multiplied by 2. So the speed here, the speed of a wave, so that's the speed, right, is equals to the square root of the tension divided by the mass per unit length. So if you want this to be multiplied by 2, so this part here has to be multiplied by 2, okay? So this is constant, so that means the square root of the tension has to be multiplied by 2, so the tension itself has to be multiplied by 4, okay? So if it's hard for you to understand, you can give yourself value, okay? You can say, let's say we start tension equals 1 Newton. Maybe the mass per unit volume is 1. Why not? So in that case, the speed will be 1 meter per second. So now you want the speed to be multiplied by 2. Okay, so that means you want that to be 2 equals the square root of the tension that will be your unknown, and then you still have 1. So you have to square both sides, so you have 4 equals t. So between here and there, you see it's multiplied by 4. So either you do it algebraically this way, or you do it here this way. So the answer is the tension increased by a factor of 4. Okay, so this one, what do they want? They want the period, so that looks easy enough. So the period, so you might think, okay, I'm going to look at the size between here and there. So maybe the period is 2 seconds. But here we have the wavelength because here is the x-axis, right? So it's a space dependence. So here the wavelength is 2. So, so here it could be tricky. It's not necessarily 2. So here from crest to crest, that's going to be the wavelength and it's going to be 2 meters. Then you know that the speed is the distance divided by the period. Okay, so the speed is 1 equals 2 divided by the period. So the period has to be 2 seconds and the frequency has to be 0.5 hertz. So you see the speed can be written as a frequency times wavelength, which is 1 meter per second. So anyway, so the answer is B, I think. Yes, 2. So here, what is the wavelength? So again, we have to be careful. This is X. So we want just the size of a cycle. So from crest to crest, that's going to be 2 meters. But if you want to find the wavelength, that's 2 meters. But if you want to find the period, you have to be careful. You have to use the speed. So here, I'm not sure I can see anything here. What do they want? What is the speed of the wave? So this is X and this is T. Okay, so that means X, you take a picture of your wave on the string moving at a given speed, and that picture will give you this, right? So again, I like this simulation here. Let's take no damping, no tension. So here you have your traveling sine wave. I stop here, I take a picture, and then this axis here will be the x-axis, and this axis will be the displacement relative to the equilibrium position. So that will be your amplitude here, maximum amplitude or the displacement y. So the distance here between here and there, that's the wavelength. Now, if you are in the time domain, okay, so that means you take that little bead here that's not going to go anywhere, and you see what's going to happen to it as it's going down and up, right? So if you take one position and you are in the time domain, then you're going to be like let's look here. So you see if you are in the time domain, so that will be the time domain, and that will be the amplitude. So you have to be very careful if you are in the time domain or if you are in the space domain. So anyway, so if you look at this one here, it's the X space domain, okay? So in that case, the distance here between here and there, it's going to be 0.6 meters. So that's going to be the wavelength. And the distance here in time, in the time domain, that distance here is 0.2 seconds, right? 0.2 seconds, okay? So the speed is the wavelength times the period, okay? So that's going to be the period. Now, just kidding. It's the distance divided by the time. So I'm going to have 0.6 divided by 0.2. So that's going to be 3. So let's go back to here. 3 meters per second. Which has a longer wavelength? So here it's not like it's a tricky equation because it doesn't behave, sound wave will not be behaving the same as light wave. Okay, so if you have the sound, when the molecules are close to each other, okay, so it will mean the sound will move faster because it will be easier for them to pass on the disturbance. Okay, so in air, the speed of sound is about 340 meters per second, and the speed in water is about 1500 meters per second because the molecules in the liquid are closer to each other. So when they vibrate, it will be easier for them to pass on the disturbance. So the answer is for the same frequency, the larger frequency, the speed. So the speed will be longer. Okay, so the speed. Okay, so the speed in water is going to be larger. So it's the wavelength times the frequency. So the wavelength has to be larger. Okay, so that means that if you have a large wave like this, of course, it's going to be able to cover more distance during the same time that if you have a small wave like that. Okay, so remember why do they ask this question? Because if you look at light, it's the opposite. So light has a constant speed. So the speed of light cannot change. The frequency cannot change. So if the speed decreases, so in water, the speed will be smaller. So that means the wavelength will be smaller. Okay. So it has the opposite behavior. So that's why it's kind of tricky. That's all. As the temperature of the string rises, the tension decreases. So if the tension decreases, so that means it will decrease the speed. Okay, so this one is interesting. So let's say you are in the ocean and you are going up and down, up and down, up and down, and there is a wave coming up here. So what's going to happen? You're going to rise because the top of the wave is coming for you. So you're going to rise and then you go down. Okay. So this one is tricky. So as the wave is moving in this direction, the crest is moving toward you. So you're going to rise. And so I found the website here and you see that's the traveling. So look, when the top is coming toward this particle here, like this, it's going up. When the throat is coming toward the particle like this one, is going down. Okay? So again, when it's here, up, it's going to go up. So that's a great simulation to understand. So anyway, the answer is up. So the speed depends on, the speed of the wave depends on the tension. So the speed of the wave only depends on the tension. So the frequency of a wave, so for a given medium, so you have to be very careful with the wording. I lost my stuff here. So look at the wording. It says for a given medium. So it means for a given tension and for a given mass per unit length. Okay, so that means the speed is constant. So if the speed is constant, so v equals lambda times f. So this is a constant here, so I cannot change that. So the frequency is the speed divided by lambda. So the frequency is inversely proportional to lambda. Okay? So these are conceptual questions, but they are not that easy. So number 24, I think this one is just plugin. So you have the density here, the mass density, you have the tension, and you have the wavelength. Okay, so let's find the speed. So the speed is the tension, so 0.4 divided by the mass per unit volume. Okay, which is turns out to be 20. Okay, because you take the square root of 400. And so the frequency is the speed divided by the wavelength. So it's going to be 20 divided by 0.2. So the speed divided by 0.2. So that's going to be 100 hertz. Because it's 20 divided by 2 is 10. 10 times 10 is 100. So what's going to happen here? So it's for the same frequency. So we are not talking about frequency. So it means you have your rope on a string. So you're gonna shake it here like this. But now you have a thick string here and then a thin string there. So we want to know what's gonna happen to the speed and to the wavelength. So let's make a drawing here. So you are shaking a string, but now you have a thick wavelength, a thick string, and then you have a thinner string, and then you shake it, so you still have something here attached, and you shake everything with the same frequency here. So the frequency is fixed, and then you send a wave, maybe you send a wave pulse. So what's going to happen to it? There was a simulation I showed you last time. I might be able to find it. So anyway, so here the linear mass here is 4 times as much. So here it's 4 times less. Okay. And the speed is, so the tension is the same. So we don't care about the tension, but we care here about mu. So if mu is divided by 4, so it has 4 times the inertia. So square root of mu will be divided by 2. So the speed will be multiplied by 2. So the speed is going to increase, right? So the speed is frequency times wavelength. So if goes up by a factor of 2, the wavelength will go up by a factor of 2. So it means if you have a traveling wave, so it's going to do traveling wave. So here you have a small wavelength, and all of a sudden you can have a large wavelength moving. Okay? there was if I can remember the website. So I found the website here, and you see that's the traveling. So look, when the top is coming toward this particle here, like this, it's going up. When the throat is coming toward the particle like this one, it's going down. Okay? So again, when it's here, up, it's gonna go up. So that's a great simulation to understand. So anyway, the answer is up. So the speed depends on the speed of the wave depends on the tension. So the speed of the wave only depends on the tension. So the frequency of a wave, so for a given medium, so you have to be very careful with the wording. I lost my stuff here. So look at the wording. It says for a given medium. So it means for a given tension and for a given mass per unit length. Okay, so that means the speed is constant. So if the speed is constant, so V equals lambda times F. So this is a constant here, so I cannot change that. So the frequency is the speed divided by lambda. So the frequency is inversely proportional to lambda. Okay? So these are conceptual questions, but they are not that easy. So number 24, I think this one is just plug in. So you have the density here, the mass density, you have the tension, and you have the wavelength. Okay, so let's find the speed. So the speed is the tension, so 0.4 divided by the mass per unit volume. Okay, which is turns out to be 20. Okay, because you take the square root of 400. And so the frequency is the speed divided by the wavelength. So it's going to be 20 divided by 0.2. So the speed divided by 0.2. So that's going to be 100 hertz. Because it's 20 divided by 2 is 10. 10 times 10 is 100. So what's going to happen here? So it's for the same frequency. So we are not talking about frequency. So it means you have your rope on a string. So you're going to shake it here like this. But now you have a thick string here and then a thin string there. So we want to know what's going to happen to the speed and to the wavelength. So let's make a drawing here. So you are shaking a string, but now you have a thick wavelength, a thick string, and then you have a thinner string, and then you shake it, so you still have something here attached, and you shake everything with the same frequency here. So the frequency is fixed, and then you send a wave. Maybe you send a wave pulse. So what's going to happen to it? There was a simulation I showed you last time. I might be able to find it. So anyway, so here the linear mass here is 4 times as much. So here it's 4 times less. Okay. And the speed is, so the tension is the same. So we don't care about the tension, but we care here about mu. So if mu is divided by 4, so it has 4 times the inertia. So square root of mu will be divided by 2. So the speed will be multiplied by 2. So the speed is going to increase, right? So the speed is frequency times wavelength. So if goes up by a factor of 2, the wavelength will go up by a factor of 2. So it means if you have a traveling wave, so it's going to do traveling wave. So here you have a small wavelength, and all of a sudden you can have a large wavelength moving. Okay. There was a, if I can remember the website, um, so here the website, you see, okay, so this is a thick one. You have the pulse here is going to thin, so it increase the size of the pulse here. Okay, so it's going to increase the wavelength, and there is even part of the wave that will be reflected. And it's the opposite in this case. When you go from fast to slow, see the size here, it's going to decrease, and some of it is reflected. So when it's reflected, you see a phase of 180 degrees. Okay, so that was for 25, which was tricky. Number 26. So it's traveling, so it's standing waves, right? So it's 20, so this is 6 meters, and this is 1/4 of a wavelength, right? So you have 1/4 of a wavelength, 1/4 of a wavelength, 1/4 of the wavelength. So if you do 6 divided by 6, no, sorry, what did I say? I forgot what I say. But this is 1/4, so it's 1/2. So you have a 1/2, 2/2, 3/2, right? So 6 divided by 3 is 2. So half of a wavelength is 2 meters. So this is 2 meters, right? 2 meters, 2 meters, 2 meters. So if it is 2 meters times 2 is going to be 4 meters. So one wavelength will be one cycle is 4 meters, 4 meters long. Okay. So pitch, we talk about that. The pitch is the fundamental frequency. The pitch is a fundamental frequency, and then all the overtones will give like instruments its tone quality. But the pitch is the frequency. So open, close. We did that in a previous lecture about standing waves. So open, close. Oh, so they want the shortest length. Okay, so one way to go with this problem, you see it's closed here and open at the end. So it means that the first here, you start here with a node. Then it's going to go up and down and up and down and up and down. So the shortest pipe here that you can fit, so it's going to fit here. And then at the end, you have to be open, right? So that means that will be L. Okay, so that will be the shortest pipe. You can fit the first harmonic inside or the fundamental. So we work about that a lot, right? So that will be a clarinet, for example, or a closed organ pipe. So that length here will be half of a wavelength. Okay, so we want to find the wavelength. So the wavelength is the speed, which is 340 divided by 218, which is 1.6 meters. Then you plug that into here. So the length of the pipe is 1.6 divided by 4, and you get 0.39 meters. Okay? Okay, so it's the same question, but now you want the second shortest. So it means a pipe which is a bit longer. So it's gonna be, you do the same thing. So you have this, so that's your wave. And the wavelength is, what did we say before, is 1.6 meters. So the second pipe, so that's your pipe, it's closed here. So that will be the fundamental. We don't want that. We don't want that. We want this. Because now it's an anti-node, okay? So this is a node. And then this one we already did. And this is a anti-node. So you see that L equals 1, 2, 3. So 3/4 over wavelength. So that's going to be 3 times 1.6 divided by 4. And the answer is 1.117 meters. Then keep going. The next one, you don't want that the next one will be this one. So that will be 1, 2, 3, 4, 5. So you see the frequency, you have F1. The next one will be the third harmonic. The next one will be the fifth harmonic. And so forth and so on. Still, this one are called the overtones, and this one is called the fundamental. Okay, so you can always pause the video. So this one is about Doppler effect that's coming up. We didn't do that yet. This one is also about the Doppler effect. This one is about the Doppler effect. This one is interesting because it's connects to mechanics. So a little bit of mechanics here. So you want to know which one, for which configuration you will have the greatest speed. So let's remember physics, mechanics, easy mechanics. So if you want to find, so the speed is larger for a tension which is larger, right? The tension in the string. So here you have the weight, okay? So that's 5 kilogram times 10. So that's going to be the tension, T. Okay, so the tension inside here will be just T, which is equals to the weight, because it's in equilibrium. But here you have still weight, but now you have two strings here. So you have T over 2 and T over 2. So the speed here, the speed will be less. Okay? Because it depends on the square root of T over 2. So here you have less speed. Here, according to Newton's third law, for every action you have a reaction, so that's going to be T here. And if it's T, it's going to be T here, and that's going to be what? If it was not, it will not be in equilibrium. So that means there is a tie between this and that. So that's called a tie. So this one, yeah, you have different ways to do it. You can do it very quickly, approximate, have a good approximation, or you can do it the long way. But the speed of light, of course, is really, 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 really big relative to the speed of sound. So here we're talking about 3 times 10 to the 8, and here we're talking about 340 meters per second. So that means 300, 1, 2, 3, 4, 5, 6. So it means if there is lighting somewhere and you are standing there, the speed of light is so large that it's going to be almost instantaneous, right? So the light will reach your eye almost instantaneously. Okay, it's in no time. Now the sound will lag behind. Okay, so the rule is when you count 5 seconds, so the thunder happened and it takes 5 seconds for the sound to reach you. So 5 seconds between the thunder, the lightning, and the sound. 5 seconds, it's about 1 mile. Okay, so that means if you count 5 seconds, the source of the sound is 1 mile away. So if you have 10 seconds, that means it's going to be 2 miles away. Okay, so 2 miles, so 1 mile, that's something to know, is about 1.6 kilometer. So 2 miles is going to be 3 point something kilometers. So the answer has to be A. Now you can do the computation instead, but it's a nice way. So you can always remember that if you have those running app, you know that 5K is 3.22 miles. Okay, so that was not bad. Number 35. Find the wavelength first. Oh, we have a hint here. Goody goody. L equals, so this is 1.2 meters. What is the velocity on the string? And they tell you find the wavelength first. So you divide by 3. So that means divide by 3, that's going to be 0.4 meters. So that means the whole wavelength here. So if you take the whole wavelength, so if you take from here to there, okay, so that's going to be 0.8 meters. So that means the wavelength is 0.8 meters. So the velocity is the wavelength times the frequency. So it's going to be 500 times 0.8. Okay, and I think the answer is 400 meters per second. So this is the answer. So this one seems a bit tricky, because if you have, it looks, it's tricky. You think, oh yeah, easy question. But remember, for a cycle to happen, so if you have a pendulum, and it's already moving here. So if you have a pendulum, to go to have one cycle, it has to go back to its equilibrium place. And so it has to go from here, and then it goes back here, soon, and then it go back to here, and then go back there. It has to finish. And it's coming back there, right? So if you only go from here to there, so then that means it's half. It's going to be half of an oscillation. Okay, so because it was already on its way here. So it goes this way up, and then this way, and then come back there. So that will be 1/2. Okay, so I found the app. So you start from here. You go to maximum height here, above the ground. Then you come back to the same position. That will be half of a cycle. And then you do the same thing on the other side. And that will be one cycle. So we already discussed that in the series about simple harmonic motion, but I will also put that link in the description. Okay, so tricky question. It was 1/2. So that's something that you should know when the two waves, so you can pause the video again, but when two waves, they move, they interact with each other. So at some point they will be at the same place at the same time, but when they pass each other out, they will retain the same shape. So that means the answer is B. So I found yet another website here. You can see that you have two waves here. They're going to interact with each other. They interact with each other and then retain exactly the same shape, and they are being reflected here. So maybe I can do something like this. And then what else can I change? And you're gonna see, poof, they pass, they maintain, they retain exactly the same shape. Okay? Now I will also put the link in the description. Okay, so this one, two wave, so you have two pulses. It's gonna be at the same place at the same time. What's gonna happen to this point here, to this particle? What's gonna happen to it? And it's kind of the same idea of this problem here. So you see, when that particle here, if it sees a crest coming, it's going to go up. If it sees a throw coming, like this one here, it's going to go down. So, okay, so look at this one here. It's coming, it's going to go up. This one is coming, it's going to go down. So whether it's going up and down depends what's coming. So if you look here, so if you look here, they both arrive at the same time because they have the same speed. So this one, it's going to see this and this. So it's going to see up here and here nothing. So it wants to go up. So it wants to go up, right? And then it's going to see this part here, and maybe this one. So this one is bigger than that part here, so it keep going up. But then it's going to see this part here versus that part here, so it's going to go down. And finally, it's going to see nothing from here, but seeing this one there. Okay? So first it's going to go up, and then it's going to go down. So also not that intuitive. It's not an intuitive question. So here, another non-intuitive question. So remember when you have a pipe here, we can look at the wavelength. So let's look at the wavelength. If we talk about the frequency, but remember, if the wavelength is multiplied by 2, the frequency is divided by 2 because wavelength and frequency are inversely proportional. Okay, so let's go back to here. So first of all, remember that you have the speed is the frequency times the wavelength. So for example, if I find that the wavelength is multiplied by 2, the frequency is divided by 2. So they want to compare the frequency in all those types. Some of them are open. So obviously, for example, here you have a larger frequency than here. And here you have a larger frequency than there. Okay. So let's do Y, CY, and CX. So first of all, if you have a closed and open pipe, remember the frequency, they go in odd number of the first one. So if you have F1, the second overtone, or maybe it's called the third harmonics, it's going to be 3 times F1. And the second overtones will be 5 times F1. And then 7 times F1. So it's not, it cannot be a even number. So that's not possible. And then they compare C, Z, and CX. So CX, you see that you can fit 1/4 of the wavelength. So that means that the wavelength is 4L. And then CZ, you have L equals 1, 2, 3, 4, 5. So the wavelength is 4L divided by 5. So to go from here to there, the wavelength is divided by 5, so the frequency is multiplied by 5. Okay, so the answer is B. Now you can do just to practice here, OY and OX. So OX. So OX, you have L equals, but that's going to be easy one, right? So that's going to be half and a half. So that's going to be 1 wavelength. And then OY, so OY, it's going to be half and then a half. So it's going to be 1.5 wavelength. So that doesn't gonna work, right? It's not working, right? So it's 1, 2, 3, 4. So that's 1 wavelength and 1.5. So that's not working also. Okay. So the answer is B. Okay. So let's try the last one. They have very interesting questions. It's a great way to practice for MCAT or epiphysics. If you change the tension of a string, It's on the guitar. You have your guitar here. I don't know how to make a guitar. Yeah, playing music here. So, what's happening? So the speed, you might have multiple correct, okay? So the speed equals, you only change the tension. So we just change the tension. So change the tension here. So you change the tension. Let's say you increase the tension. So what's going to happen to the speed? You're going to change the speed for sure. Okay. So the frequency, you remember we did that in standing waves. When we did standing waves, so it's going to be something like this. So you don't change the L. And if V, for example, if you increase V, so the speed is going to increase. So it means higher tension. That means larger pitch. Okay, so higher frequency. So you're going to change the frequency. If you take the wavelength, it's going to be speed divided by frequency. So it's going to be V, and V times 2L. So no, it's not going to change. Okay, so that means um, the frequency. So you are changing the speed and you are changing the frequency. You are not changing the wavelength. Okay, so for those who play guitar, you already know that. You don't need the physics for that. Okay, so next time we'll talk about sound, and we'll talk about sound.